right? So this lesson is called function operations. And the thing about it is that the first four function operations are addition, subtraction, multiplication, division, things that you're pretty familiar with, and they don't work much different with this than what you would have thought. If I ask you to guess how it's going to work, it pretty much works that way. The difference with this, the thing that starts to become more challenging and more important is that we really have to start getting at this concept of domain. You know what domain is. You've done domain before. But domain, when it comes to dividing functions or doing operations with functions, is a little more complicated than the just plain old, here's a set of points, find all the x values. So that starts to become a bigger deal right here. Then there's this fifth operation that is not something that you've seen before. It's not like anything that you've seen before. Right? So the first four, I think you're going to think are pretty much like you would have thought. But the last one, you got to learn a new thing. Right? So first of all, the add, subtract, multiply, and divide of functions. The notation is like this, right? In one set of parentheses, it's f plus g, okay? And then end parentheses, and then parentheses x, right? That's function notation. I mean, we've done function notation before, f of x, right? F of x, right? That's the same thing that's going on here, right? This is, let me write it up there. That is f plus g of x, right? It's not a multiply, right? So when you're going through this stuff, you don't want to be looking at, oh, I'm going to add the f plus g. Oh, but there was this last step of multiplying everything by x. That's not a multiply by x, right? That's just like saying f of x, right? We know when we say f of x, that doesn't mean f multiplies x. It's just one whole thing, right? That's what this is. It's the way we write function notation for that. Right? It says not, I'm going to put that in red, not multiply. Now, it doesn't matter which one of these operations you do. You usually don't leave it with f plus g in parentheses of x. The very first thing you're going to do anyways is rewrite it as f of x plus g of x, which is the function notation that we're used to. Right? Or f minus g of x is f of x minus g of x. Right? F times g of x, and that dot is being used as a multiply between the two functions. Right? Of x equals f of x times g of x. And the divide, f divided by g of x is f of x divided by g of x. Now, here's the important part. G of x does not equal 0. And this is where we have to start talking about domain. Right? We know there's a couple things that you're not allowed to do. And that, when it comes to domain. And that one of them is you can't divide by 0. Right? You're not allowed, in math, you're not allowed to divide by 0. Doesn't work. Try it in your calculator. What do you get when you divide by 0? Error. Right? It's an error. So you can't do that. So we're right here, if we're dividing by a function which could equal 0, we've got to start becoming concerned about the domain of this f of x over g of x. That's why they put that right there. Right? And then we will have to start looking for, what are the x values that make that true, because we got to make sure they're not in the domain. So we'll talk more about that in a second. But the first four operations, again, are basic operations that if I ask you how you think it ought to work, it works exactly like that. So here's two functions that are defined for us, right? F of x and g of x. And it wants us to find the f plus g and the f minus g. Okay, so just using their definition, f plus g of x equals f of x plus g of x. Okay. Now we're going to replace the f of x with what it equals. Right? This 4x plus 7 goes here in the place of f of x. And g of x equals that. right? That's all they've done to go from this part to this part. They've just replaced each with what it equals. Okay, and then they combine like terms. Right, it looks like we've got a 4x plus x. That's where the 5x comes from. Right, the square root of x, right? The square root of x and 5x are not like terms, right? They are not the same variable raised to the same power, so you can't combine them. Again, this almost confuses from what we just did about like terms and like radicals. But remember, you got a thing that connects those two, and that's the rational exponents. I mean, I could write this here as 5x plus x to the 1/2 plus 7, right? Because we know that the square root of x is x to the 1/2. Now everything is in terms of exponents, right? These are not like terms because they don't have the same variables raised to the same powers. So you can't combine those. You just have to, sometimes these things, there's not a lot of simplifying really you can do. You just need to put them together the best you can. Now, the subtraction is a little more fraught with difficulty than the addition is. And I'm not even sure that they've done a good job of showing that here. But if you do the f minus g of x, again, that's f of x minus g of x. We are going to replace the f of x with 4x plus 7 and the g of x, with the square root of x plus 7. But here's where we always make a mistake with that. Because you're subtracting more than one term, you've got to remember that this minus distributes on both terms in that second expression. So we could write an intermediate step that looks like this: 4x plus 7 minus the square root of x minus x. And then that would definitely get us to the right thing. 4x minus x is 3x. I'll say that out of all students, probably when you see that kind of question on the test, half of you will not do that one step. You just say minus the square root of x plus x, and you'll end up with 5x here because you didn't flip the sign. Right, so if I would have asked you about that, how do you think it would work to add or subtract? That's probably what you would have guessed, right? And you would have been right. Jose, right? Okay. Now, I'm going to put up now that you try it, okay? Try to do the same thing with this. Here's the thing about this now, change of procedures, partly because it's being top-down driven on me, and partly because I was thinking about this anyways. Do this on a separate piece of paper, and I'm going to be picking these up at the end of class. So it'll have its own classwork credit. So try to do this one. Switch planning. What's past? I'm here at 7. Again, the addition will probably go pretty straightforward. So subtraction, you got to be a little more careful when you're subtracting more than one term. How many have finished the addition one? No? Yeah, you finish it? Let's see what you got. Squared plus x plus 5. And the other one, 2x squared. What happened to the x? Okay. So when you did the addition, which were the like terms? The constants. The constants, right? So other than that, I mean, you're just going to write this as 2x squared plus x, and 8 minus 3 is 5. And remember that simplifying means it includes writing it in standard form, right? Making it a highest power term on the left, descending order of powers. So now how does that change when we were subtracting? Now it's 2x squared plus 8 minus x minus 3. Which you could either write it as a separate line like I just did, or if you're good with it, just say that's minus x plus 3 directly, because you see that it's going to flip all the signs. So we're going to get a little bit different combination of the like terms now. That'll be 2x squared minus x plus 11. Easy, right? I hope so. Let's go to the next. Right. Multiplying functions. So again, according to that first slide that showed us how these things work, when you've got the f dot g in parentheses of x, then how do we rewrite that? We write it as f of x times, with a dot, g of x. And then what do you think we would do from there? Replace each one with what it equals, right? So now we're going to take this, whatever the f of x equals, we'll put it in the place of the f of x here. And whatever the g of x equals, we'll put it in the place of the g of x here. Right? What is that going to look like? X minus 2 times x plus 3. All right. Now that would not be simplified. How do you simplify? Yeah, you're going to have to FOIL it. So FOIL it. X times x, x squared. X times 3, 3x. Negative 2 times x, and negative 2 times 3. Combine like terms. I mean, again, if you had to guess how this is supposed to work, you'd probably guess that's how it works, and you'd be right. Somewhat intuitive. Okay. So try that one. Remember, same piece of paper which you can hand in at the end. Oh, I didn't even write this down. Try to do the f dot g of x. What'd you get? Anybody? Say again, Jaden? X squared minus 25, right? I mean, it's x plus 5 times x minus 5. Right? So this is just writing the step, which maybe you'll skip writing it like this, but that's okay. I'm just going to include f of x times g of x, which is x minus 5 times x plus 5. And again, if you FOIL that, you're going to get x squared minus 25. Okay, if you look at x squared minus 25, that's the difference of squares, and that's how it factors. So you may not even FOIL it. You may just say, I know what that equals. That's the multiply. So we've done add, subtract, multiply, and we've got to do the divide. Again, the divide is where it starts to become a little more tricky. Not so much for the divide part, but because of domain. And so we already got on the first slide, it told us if you do the f over g in parentheses, you're going to rewrite that as f of x divided by g of x, right? Which is x plus 4 divided by x squared minus 1. Many of the time, most of the time, not a good part of the time, when you do this with the divide, there's not a lot of simplifying you can do. This one, there's nothing you can do to simplify. I mean, just at the very least, just write it like that, right? If there's some simplifying that goes on later, that's okay. I mean, maybe you'll miss that part, but that shows you understand how it is you divide functions. Just show that step. Okay, now this is where it gets into the domain part. We are not allowed to divide by 0, ever. But is it possible? Are there some x values for which x squared minus 1 equals 0? Yeah, there is, right? I mean, let me check something here. I'm not sure if I wrote this on another slide. No. We have to make sure that x squared minus 1 does not equal 0 for our domain. So what we're trying to find here are the zeros of the denominator. right? And that's something that should mean something to us from chapter 5, right? The zeros of the denominator actually, now I remember what I was doing here. We're going to talk about domain first. Before we add that, I've got this copied later on. We know up till now, domain has meant the x values, right? If you're given a set of points, domain meant take all the x values and put them into one set. And yeah, in chapter 2, we put them in order, no repeats. That was part of it. But that's what domain meant up till now. Okay, when you're dealing with functions, functions have graphs, and graphs are made up of infinitely many points. There's no way you can write down a set of points and then just take all the x values and say, that's my domain. So instead, we state the domain of a function by describing the x values that we're allowed to substitute for x. You know, what is it that we can plug in here and not cause some mathematical disaster, right? I mean, what value of x would lead to this function having a divide by 0? What would x equal that would cause you to divide by 0? How about x equals 0? Right? If x equals 0, you're dividing by 0. So those are the kind of things that you've got to look out for. And when you're dividing functions, since the function could equal 0 most of the time, not always, right? But if the function can equal 0, then you're going to have to figure out what are those x values. What are the zeros of the denominator? Because that's how you're going to describe the domain. Right? So the way we describe the domain is we're always going to say it's all real numbers. The starting point is it's all real numbers. Right? Then you're looking for two situations, at least at this point, there's only two situations which we would say, but not those x values. One of them is x values that cause a divide by 0. Right? The zeros of the denominator. Whatever the zeros of the denominator are, you have to take those out of the set of the domain. Another one, and this is kind of pertinent to this chapter in particular, is, you know, you can't take the square root of a negative number. Remember when, again, just like we did on our test just now, if you have a square root of a negative, you just say non-real and you walk away from it. Same thing here, right? If we have a square root in a function, you're going to have to say something about the domain being limited. It's not all real numbers anymore because you can't plug in negative numbers. So these are the two exceptions to the all real numbers for the domain. And in fact, the square root of a negative, and more generally, even roots of negative numbers would not be allowed. Okay, about ready. Good, Denise? Okay, so that same problem right? We already got to this point here. We had x plus 4 over x squared minus 1. Now we need to know what are the zeros of the denominator. I mean, set the denominator equal to 0 and solve. X squared minus 1 equals 0. You could solve that like the second test question, right? You could get the 1 on the other side, and then what? How do you make turn an x squared into an x? You take the square root of both sides, right? So, and when you take the square root of 1, we say is plus or minus 1. Remember, when you take the square root, you need the plus or minus. So the zeros of the denominator are x equals 1 and x equals negative 1. So the domain is all real numbers, means I can plug in any real number for x, all real numbers except x equals 1, x equals negative 1. You know, remember, x is considered the independent variable. Remember, when we make a table of values, it's always the question, where are you getting your x values from? You pick them. You get to pick them. The domain is telling you which numbers can you pick from, right? In this case here, you can pick from any real number, but just don't put in 1 or a negative 1. That's what the domain is. Now, most of the time, the way you would write this as a domain is you would do this. X does not equal plus or minus 1, something like that. You wouldn't necessarily have to say all real numbers except, you just say x does not equal that number and that number. And that implies it could be anything else. That's a really poor not equal to. Okay, so here's another one. Just to show you, now we're doing g over f of x. And again, this time we're going to state the domain. Okay, g over f of x will be g of x over f of x, which is x squared minus 1 divided by x plus 4. Okay, 0 of denominator. This time I'm saying singular, because what is the one value of x, which is going to make that denominator equal 0? Not 0. 0 plus 4 is 4. What value would you substitute for x to make x plus 4 equal 0? Negative 4. So how would you state the domain? X does not equal negative 4. Right? If the 0 of the denominator is negative 4, then the domain is x does not equal negative 4. It's all real numbers except negative 4. Good. So try that one. Try to do this f of x divided by g of x and state the domain. Okay. You're getting the solution. What do we get for a domain? What does x not equal? -6, right? So we have f of x over g of x equals x squared minus 3 over x plus 6. The domain is x does not equal -6 because that's the 0 of the denominator. Okay, that covers our add, subtract, multiply, and divide. Again, for subtraction, you got to worry about if you're subtracting more than one term, you got to flip the sign of every term. For division, especially, you got to worry about domain. If you're dividing by something that could equal 0, then you've got a restricted domain. Okay, and if I go back to that first adding and subtracting of fractions, there actually was a part to that question which I had erased before, but it did say what's the domain of these adding and subtracting. Now, there's no dividing going on, so you don't have to worry about dividing by 0. But what is there going on? Remember, there's two circumstances that you're trying to make sure that you don't do. You don't want to divide by 0, and you don't want to do what else? Madison's looking. A square root of a negative, right? You got a square root. Right, so for this one in particular, if I was going to say the domain of this, I would have to say, well, we're taking the square root of x. So the domain has to be x is greater than or equal to 0. Right, because of the square root, the domain is x greater than or equal to 0. If you tried to plug in a negative number into these functions right here, when you got to that one term, it would be undefined. It would be non-real. So those are the two situations we worry about now. Right? Divide by 0, square root or even root of a negative. Okay, that's the same slide that we had before. I just added the domain part. Now, composition of functions, this is a new one. This was not one that you might have some intuitive sense of how you might do that. Okay? The composition of functions is like putting one function inside of another. You know, for example, here's my if I have an f of x and a g of x, it's like taking that entire f of x and put it inside the parentheses for g of x. So what does it look like? It looks like g of f of x, right? Taking that whole thing, put it inside. That's a composition. You could do it in either direction, right? You could stuff f into g, or you could stuff g into f. Either way, that's called a composition. You know, there's ways that we'll explain this, but I find that for the most part, if you just understand that part of it, that you can get these right most of the time. So for example, let's say we have f of x equals x plus 4, g of x equals x squared. Right? If I put the f of x into the g of x, this is what it looks like. Right? It's like you're taking this x plus 4 and you're putting it in the place of x in the other function. So what does that look like? It looks like x plus 4 squared, right? It's the f function squared. That's g of f of x. Now, when it comes to doing a composition, if you get to this point where you've done that, I mean, you could leave it like that. I mean, yeah, I mean, if you were going to simplify, it would be x plus 4 times x plus 4, and you'd have to FOIL it. But if you guys leave it like that and just get that far, that's safe. Now, if you choose to FOIL it or if you choose to simplify, just make sure you get it right. I mean, you can't go on the next step and say x squared plus 16, because it's not, right? It's x squared plus 8x plus 16 if you FOIL it. So you're all right to just leave it like that. Right? Now, it would look different if we went the other direction. If I put the g of x into the f of x, that means take this x squared and put it into the place of x here. And that looks like this. Does that look the same as when we did g of f of x? G of f of x was x plus 4 parentheses squared. It's not the same. Which tells you that the order that you do a composition matters. Which means commutative property does not hold for doing compositions of functions. The order matters. Good with that? Okay, now this is the graphic from the book. Now most, just like we had like a different notation for the add, subtract, multiply, and divide, there's actually another one for the composition too. It's like g of f of x is usually written like g and a little open circle and then f parentheses of x, like that. And you got to be clear, like, don't confuse that little open circle with a multiply, because we know that's how they show a multiply, is with a dot. That's not a dot, it's a little open circle. Right? So, and the way you would read this, whether you write it like this or like this, the way you read it is like this: g of f of x. You could almost look at that little open circle like an O. G of f of x. And again, that's not a multiply, right? That's between those two parentheses, that's not a multiply. You don't have another x to throw in there in the last step. Okay. So let's do a g of f of 2. And we're going to do it two different ways. If you look at the book example, which is not exactly this example, but they do two different ways. The first way is find g of f of x. Okay, well, g of f of x would look like this. G of f of x would be g of f of x. Right? We always end up rewriting it like that anyways, if you get that little open circle. Sometimes it's just given to you like g of f of x, and sometimes you got to like put it into that form. Now, if we're going to put the f of x inside of the g function, that means take this and put it in the place of x there. What does that look like? What will it look like if I take this x minus 5 and I replace the x with it? X minus 5 squared plus 1. Right? You still got the plus 1. Okay, now if I want to do the g of f of 2, right, then g of f of 2, then, how do we evaluate a function? We say, here's f of x, find f of 2. What does that usually mean? Just substitute x equals 2, right? So in this problem here, it'll be 2 minus 5 squared plus 1, which is negative 3 squared plus 1, which is 9 plus 1, which is 10. So in this way of doing it, we found the g of f of x first, and then we evaluated for the x equals 2. Okay, that's probably not the way you're going to want to do your homework. You're probably going to want to do it like the second way, where I'm going to show you right now. We good? Okay. In this way of doing it, first I'm going to still rewrite it as g of f of 2, like that. Okay. And now find f of 2. If f of x equals x minus 5, what is f of 2? F. Just fine. Use this function right there. If f of x equals x minus 5, what is f of 2? 2 minus 5, right? Just plug into this function only. Plug in x equals 2. And so this equals negative 3. Okay, so now we can replace this f of 2 with a negative 3. So this is g of negative 3. And then now use this function right here. If g of x equals x squared plus 1, how do you find g of negative 3? You plug in negative 3 here, right? Negative 3 squared plus 1, which is 9 plus 1, which is 10. And so you don't ever make that g of f of x function. You never have to put one function inside the other. Just evaluate the inner function first, and then evaluate the outer function with whatever results you got. And all of the homework problems are like that, where you can do it just like that. So that would be more like this. Evaluate the inner function right, and then evaluate the outer function. I think if you look at the graphic that we had up a couple slides ago, that's what they say. Evaluate the f of x first, because that's the inner, and then use that to evaluate the outer function. So that's pretty much what they had on their slide. So like I said, I think you may find that easier. I mean, there is a place for us to have to find the g of f of x without actually just stuffing numbers into it right away and avoiding that step. But for right now, we'll just worry about that part of it right here. So I think there's one more you try. Right? Try to do I think these are the same functions. It's just I flipped the order. Instead of doing g of f of x, now we're doing f of g of x. Anybody got an answer? Shannon? Christian? What'd you get? 0? Does anybody else get 0? The answer is 0. I mean, again, this can be done really quickly, right? G of 2 is 2 squared plus 1, 5. F of 5 is 5 minus 5, 0. Done. That's the whole thing. Right? So rewrite it as F of G of 2. Right? G of 2 equals 2 squared plus 1 equals 5. Right? So that is F of 5. What you got? Okay, thank you. And that is 5 minus 5, 0. So that's composition of functions. Again, we just did that. We did the opposite. We did G of F of 2, and we got 10. We did F of G of 2, and we got 0. Order matters, right? So now let's see. Identify domain, range zeros. Right. So this is getting at the domain. And describe restricted domains. Okay, that's divide by zeros, square roots of negatives, and find the composition of two functions. Those are the SOL essential skills that we're supposed to be touching on. And the homework here, right, both sets of these are alls. Right? These are add, subtract, multiply, divide. These are the compositions. This should work just like the last example. I think in the book they have a different example altogether. So if you wanted to look there, you'd have another example of it.